My project focuses on the optimization of an ultrasonic atomizer for droplet ejection and particle focusing. My name is Andrew Ledbetter. Acoustofluidics combines ultrasonics with microfluidics and allows for the powerful manipulation of fluid and particles on a microscale down to the nanoscale. The figure on the right shows a typical microfluidic channel that is in between two piezoelectric transducers, and figures A through F show the fluid velocity field as well as some particle focusing, and just shows that you can have uniform flow, strongly mixing flow, or just particle focusing and particle trapping within the fluid, just based on the pressure field generated within the fluid. So my project will focus specifically on the geometry shown at the right, which involves fluid reservoir that has a rectangular fluid reservoir that has pyramid-shaped nozzles at the top surface. From bottom to top, there's a piezoelectric layer, an aluminum coupling layer, then the fluid reservoir, and at the top there's the silicon chip that has the pyramid nozzle etched into it. The device generates a standing focused acoustic pressure field within the fluid reservoir, and it has two main uses. One, it atomizes the fluid, creates droplets that are on the order of diameter of the nozzle, typically about 40 micrometers. It also focuses particles that are suspended in the fluid reservoir. There are many applications to this kind of a device, including cell separation, inkjet printing, and fuel atomization, and many others. So the pressure field is what drives all the operation of this device. And it's characteristic of the thickness of each layer as well as the driving frequency of the piezo. So I'll show this video, which is a frequency sweep at one specific geometry. So the red is high pressure and the blue is almost zero pressure. The pressure peaks are typically on the order of 1 megapascal. And so I just swept through a frequency of 0.5 megahertz up to 2 megahertz. So the droplet ejection the fluid atomization is driven by the pressure gradient at the nozzle tips, and the particle motion is driven by the acoustic radiation force, which is a function of both the pressure amplitude and the pressure gradient. So why there's a need for optimization of this device: fabrication is very expensive, and there's very high precision required to match the layers so that the pressure field is at a resonance. Setup and experimentation are very time consuming, so you couldn't change the thickness of each layer by 1/10 of a millimeter and retest it. It would just be very time consuming, very expensive. What's useful is we can simulate the device using finite element analysis, such as ANSYS, that has a harmonic analysis package. There are also analytical expressions that have been developed to predict resonance for rectangular cavities. And so since our cavity is almost rectangular, just with the nozzles added on, we might be able to predict some optimization geometries just based on those analytical expressions. So the two goals are to maximize the nozzle tip pressure gradient so that we have the strongest ejection of droplets, and the second optimization goal would be to maximize the acoustic radiation force throughout the fluid reservoir. There's more details on that in the document I'm submitting. Thank you for your time.